Weight, which I'm going to symbolize Fw, is gravity's effect on an object. The weight always acts downward. So if we have a mass on a horizontal surface, that mass has a certain weight acting downward. If that mass is on an inclined surface, say inclined at an angle theta above horizontal, again, the weight of that mass always acts straight downward towards the center of the Earth. The equation for weight is a very simple one. It's m times g, where Fw is the weight in newtons. Newtons is the standard unit for force in the SI system. M is the mass in kilograms, and g is the acceleration due to gravity, typically on Earth. That's going to be 9.81 meters per second squared. You may have seen g as equaling negative 9.81 meters per second squared. I'm going to use it as a positive number with the understanding that the weight force always acts downward, and that takes into consideration that negative sign that you might have seen earlier. So, weight is m times g. On incline problems, it is convenient to resolve all forces into perpendicular and parallel components. For the weight Fw, you can see here that we have a mass on a surface inclined at an angle theta relative to the horizontal. The weight acts, as always, straight down, and it's numerically equal to m times g. However, when we get to later lessons in this unit, we'll find that that particular force, whatever number that is not very convenient. What we'd rather have is the perpendicular component of that weight and the parallel component of that weight, which I've called Fw perpendicular and Fw parallel. Fw parallel will be found by taking the weight times the sine of theta. You notice that Fw parallel is opposite this angle theta. So Fw parallel is equal to mg sine theta. Fw perpendicular is equal to mg cosine theta. This angle of incline, theta, turns out to be exactly the same angle right there between Fw, which is straight down, and Fw perpendicular, which is perpendicular to the surface. We could take some time to show you that, but I'm not going to go through it. Convince yourself of that if you wish. If this were a problem that we're going to do later on in one of these lessons, this vector mg cosine theta would be a very handy vector, and this vector mg sine theta would also be a very handy vector. The normal force, which we symbolize F sub n, is the force a surface exerts on an object, normal, that is perpendicular to a surface. So in the leftmost case, we have a mass sitting on the table, and it's held in place by a normal force, which is numerically equal to its weight, m times g. So in this case, on the left, m times g downward is numerically equal to the normal force upward. You notice that I've drawn those arrows the same length. In the middle picture, let's say I push down on the mass. This is an applied force, F sub a. So not only do we have the mass sitting there, but now I'm also pushing on it. Well, when I do that, the table needs to push up greater than the weight of the box. In particular, if the box stays put, then the normal force will be equal to the weight plus the applied force. So I've tried to make the normal force arrow equal in length to the sum of those two. Similarly, if I, in the rightmost picture, pull up a little bit on the mass, now not enough to lift it off the table, but if I pull up on it some, then the normal force is actually less than the weight. And that's because in order to hold this mass up, we need the table pushing up somewhat, but then I'm helping the table, so the table doesn't have to push up as much. It's a common mistake for students to think that the normal force is always equal to the weight, and that is definitely not the case. Down here at the bottom of the screen, the normal force changes with surface angle and with applied force, but the weight stays constant. So if I push down on the mass, the normal force will be equal to the weight. If I pull up on it some, then the weight will be less than the weight. And that's because in order to hold this mass up, we need the table pushing up somewhat, but then I'm helping the table, so the table doesn't have to push up as much. It's a common mistake for students to think that the normal force is always equal to the weight, and that is definitely not the case. Down here at the bottom of the screen, the normal force changes with surface angle direction and magnitude, but it remains at right angles to the surface. So if we have a mass on an incline, we talked in the previous slide how the components of weight would be mg cosine theta in that direction and mg sine theta parallel to the surface. In this case, the normal force remains normal, that is, at right angles to the surface, and it would case numerically equal to mg cosine theta. Let's summarize forces too. Weight is the gravitational pull on an object. It always acts straight downward, but can be resolved into components for ease of use in solving certain problems. And here's the equation for weight, m times g. The m has to be in kilograms. No other unit is acceptable. G on Earth is 9.81 meters per second squared. The normal force is one force a surface exerts on an object. It is always perpendicular to a surface, no matter the orientation of the surface.